subgroup if it's a subgroup, and which is respected by, can I move that? No, I can't. Which is respected by n. Could you move it up a bit, please? Yeah. In this case, this delta is a delta module itself. We distinguish between n subgroup and n submodule. An n subgroup is an n module which is contained in the bigger n module gamma, and the n submodule is the kernel of an n homomorphism. In the non-commutative case, we have to distinguish between subgroups and normal subgroups and subgroups and kernels. Well, we already had the characterization. Please, how can we characterize an n submodules? It's clear the kernel of an n homomorphism must be a normal subgroup, and I like to formulate it this way: if gamma 1 and gamma 2 are congruent modulo this normal subgroup delta, that means that gamma 1 minus gamma 2 is in delta, or the other way around, then this congruence is respected by multiplication, by the application of an element of n. This is true for all gamma 1, gamma 2, and all n in n. Well, explanation: gamma 1 congruent gamma 2 means that the residue classes modulo delta are the same, left or right. We may reformulate this. This 2 means that gamma plus delta n minus gamma n must be in delta. That's exactly the stability of this congruence modulo delta for all gamma delta n. And it's clear if delta is a submodule, not a subgroup, not only a subgroup, a submodule, then we might form the quotient, the factor n module, and it's clear how we have to apply the reaction of n. And the canonical homomorphism, call it H, of gamma to gamma modulo delta, is an n epimorphism. Once more, we have to distinguish n submodule and n subgroup. An n submodule of gamma is an n subgroup. The other way round is, of course, false. Let's look at a few examples. Let gamma be any group. Remember, our title was group mappings, so we do not specify our group, or we do not need to specify our group. Must be for a large variety of groups, what we do. If we consider the nearing of all self-maps of gamma into itself, which leaves of all self-maps of gamma, gamma into itself, which leave the neutral element of gamma fixed, then this M0 is a Near-ring, and moreover, it is the zero-symmetric part of a larger Near-ring, namely the Near-ring of all self-maps of gamma. And if N is a sub-Near-ring of this M0 gamma, then gamma is a, gamma is an M module, which M is abbreviation of M0, and an N module. So this is true for any group. And then the next thing is true for any Near-ring in our sense. We consider the additive group of N, and this is an N module by right multiplication. X, comma, N goes to Xn. The N subgroups of N plus of this N with respect to addition are subgroups R with a property that Rn is contained in R. Now, what about the N submodules of N plus? Well, they are what we call right ideals. We define right ideals as N submodules of N plus, which means that R is a right ideal of N if and only if R is normal subgroup of this additive group of N. And N plus R times M is equal to Rm. No, N plus R times M minus Rm is contained in R for all Mn in N and R in R. We are accustomed to, from ring theory and module theory, to compute in various ways with submodules. Quite a few things might be copied. Let gamma be an N module and consider two submodules, delta and epsilon. This is supposed to be Greek epsilon, are submodules of gamma. Then we may form delta plus epsilon, and this is again a submodule. Proof is relatively easy. We had this in R3. This is a characterization of submodules. We know from group theory that this sum must be, again, a normal subgroup of gamma. And take an element from delta plus epsilon, small delta plus small epsilon, and gamma plus this delta plus epsilon, and apply N. First, we change the brackets, and then since epsilon is a submodule, we have this is gamma plus delta N plus epsilon 1, and gamma plus delta N is gamma n plus a suitable element delta. And if you put this together, we have gamma plus delta plus epsilon n is gamma n plus an element delta 1 plus epsilon 1 in delta plus epsilon. Let us consider the set of all n submodules of gamma. Then intersection and this definition, which we defined already, then this is a lattice. And in fact, the sublattice of the lattice of all normal subgroups of the additive group gamma. The next subsection C is a bit, well, is a bit out of order just at this place, but I found out that I need it, and so I put this definition here. Gamma, I call gamma monogenic. People quite frequently say cyclic, but my supervisor could be, when I was young and did my thesis, my supervisor was absolutely against cyclic because that has nothing to do with a cycle. Monogenic comes from the work of Bourbaki, monogene. It means generated by a single element. Gamma is called monogenic if there is a gamma 0 such that gamma is gamma 0 times n. And of course, this gamma is called a generator. It's a generator in a very special sense, generator by application of n. Then we need, at certain point for the further discussion, we need the concept of a subnearing S of n to be left invariant or two-sided invariant. In the first case, if n times S is contained in S, or if both relations are to ns contained in S and Sn in S. Yeah, this is, well, just a word. The kernels of the nearing homomorphisms of N are called two-sided ideals, nearing homomorphisms, not nearing module homomorphisms, are called two-sided ideals. The ideals 0 and n are called trivial ideals. Any ideal of n is a two-sided invariant subnearing of n, and the ideals of n are precisely the left invariant right ideals of n. Now, for our further consideration, we need annihilators. If you are given a subset of delta of gamma, then the annihilator of delta is defined to be the set of all elements of n, such that delta n is 0. This is, yeah, if delta would be one element, then it's obvious to compute that a small gamma is a right ideal and a capital delta is a right ideal. That's an intersection of many right ideals. If delta is an n subgroup of n, then a delta is an ideal. Well, very simple. Let's consider the case that gamma is monogenic with generator gamma. Then we might consider the obvious epimorphism from N plus to gamma, N going to gamma N. This is an N epimorphism of N plus onto gamma with kernel A gamma. Clear. If gamma equals small gamma times N is not only 0 and gamma has only the trivial N submodules, O gamma or omicron gamma and gamma, then A gamma is a maximal proper right ideal. There is a, you might you might define a correspondence between right ideals between A gamma and N plus, and this is mapped onto gamma, and if gamma has known on the submodules of gamma, and if gamma has only the trivial submodules between A gamma and N plus, can be no right ideal. Now, so far, N was nearing and gamma was a group, and N acts on gamma. We look for a technique to identify these N's, the element small n of with self maps of gamma. For this purpose, we defined an N module gamma is called faithful. But faithful if the annihilator of the whole of gamma is 0. This is an ideal, and N modular A of gamma is isomorphic to gamma in the module sense. If gamma is a faithful N module, then N is isomorphic to a sub-nearing. Yeah, if gamma is faithful, then N is isomorphic to a sub-nearing of M0 gamma, which means a nearing of 0 fixing mappings of the nearing of all 0 fixing mappings of gamma into itself. And hence we can identify N with a mapping gamma to gamma, gamma, small gamma going to gamma N. Let me look at it from a different point. Gamma faithful means if gamma M and gamma N are identical for all small gammas in capital gamma, then the difference of M minus N must be in the annihilator of gamma, which is 0. Hence, M is equal to N. We apply this to the following lemma, which will be useful later. Let N have an N module gamma with the following properties. First, gamma is faithful. Gamma is commutative as an additive group. And for all n in N, the mapping gamma to gamma, for all n in N, the mapping gamma to gamma, small gamma going to small gamma times n, is an endomorphism of this additive group. Then N is a ring. It's not difficult, but let's give the proof. We apply what we did before. Let Mn and R be elements of N. Then for all gamma, small gamma, we have gamma times N plus M. This is gamma N plus gamma M. But these are elements in capital gamma. And so by our assumption 2, we can interchange the order. And then this is, well, gamma M plus gamma N is the same as gamma times M plus N. And this is true for all gamma. And capital gamma is faithful. Hence, N plus M is M plus N. So we have commutativity of addition. And the next thing what we have to prove is the missing distributive law. So let's start. We consider N plus M in brackets times R, and we apply this to gamma. Then we have gamma N plus gamma M times R. And now, according to our assumption, this R, they're mapping this R must induce an endomorphism of gamma plus. So we have gamma N times R plus gamma M times R. And this is the same as gamma NR plus MR. And we see this is, since this is true for all gamma, small gamma, and capital gamma is faithful, we have the second distributive law. One implies N plus is commutative. 2 implies we have the missing distributive law, and this completes the proof. Yeah. Since we have to distinguish carefully between the N submodules and N subgroups. It turned out to be advisable to distinguish certain situations, and this is done by distinguish certain types of N modules. Not you could define gamma times M to be the 0, then that's not interesting. We have to avoid this. Gamma is called of type 0 if it is monogenic by a suitable element. I do not say what the element is monogenic and has only the trivial submodules. In ring theory, one would possibly call this as irreducible. It's of type, yeah. The counterpart would be it has only the trivial N subgroups. This is type 2. Type 1 is in between. Gamma is of type 0. What we defined. And for all gamma and gamma, we have gamma n is gamma or gamma n is 0. That's more, yeah, that's more than no n sub, proper n submodule. Type 2 means gamma has only the trivial n subgroups. So it's as an n module, it's minimal. And we call the nearing new primitive on gamma if gamma is a faithful n module of type n. Note, gamma must be faithful, a faithful n module of type n, n being 0, 1, or 2. And we call n new primitive in general if it is new primitive on some gamma. Just a moment. Yeah. So we have defined new primitive near-rings, and our goal is to investigate the structure of the new primitive near-rings and combine them with the group mappings. Now, let n be a nearing and gamma an n module, then the n endomorphisms of gamma form a monoid. It's clear. You might just by composition, you form you form a monoid. The identity mapping, the identity endomorphism is the identity element of this monoid. And it's a monoid with a 0 element, but you can have the endomorphism which maps everything to 0. It's a monoid with a 0 element with respect to composition of mappings. This monoid C is called the n centralizer. I should have made a bit more of these charts, but I can now explain what we are going to do. What we intend is a description of zero primitive near-rings. And for this, we need to restrict ourselves to such an action which commutes with the n endomorphisms, and our goal is a density theorem which allows to identify n with m0 times gamma, m0 times gamma. In other words, we want the situation that given in a certain sense, minimal gamma, and a new primitive nearing on gamma, and we want to identify this with our M0 of gamma. What we I'll give the, if I would be in front of a table of a blackboard, I could write it down. We will give these charts next time in a week. We can study first a few examples, and then our main theorem on this in this context would be a density theorem, which allows, under certain minimality conditions, to identify n with M0 gamma. Yeah, I apologize for not having prepared more charts. I'll make this up next time. Sorry. So we meet again in a week. Goodbye.
Okay, thank you very much. And there's no problem if you stop a little earlier and you send me the files for next time then. And before you close, I have a interesting and a very pleasant news for all of you. There will be pretty soon, there will be a new book on Near-rings out with Springer Verlag, and this is just a very new message I got on the weekend. The author of this book is Bob Lockhart, which was a big surprise for me because I didn't hear from him for quite a long time. But now he has come up with a long book, a nice book on nearings, and this should appear already at the end of May. So it was a big surprise to get this message. Well, thank you very much for being here again, and hope to see you again next week.
Yeah. Goodbye.
Thank you.
Goodbye. Voilà.
Can I ask you a question, Gunther?
Yes, sure.
I wanted to know if these slides that you project, you can send them to us.
Yes, that was our intention, and I would like to discuss it with Betsch.
Oh, yeah, you just exited, yeah.
Yeah,
Oh, for sure.
that's our plan anyhow, but I think he had forgotten to do it up to now, but there's no problem to send it to all of you.
Okay, thank you.
Okay, thank you. Oh, Bernardo, may I ask you a favor?
Yes.
I usually forget to push the record button in time, so I always discover it a few minutes after the start.
Yes.
So if you act as my external memory and remind me of this.
Yeah, I wrote to you today, but I was 2 minutes late too, so.
Okay. Well, okay, fine.
Okay, for sure. Goodbye.
Goodbye.